Okay, so now we're gonna discuss what's this stress distribution uh, within a power screw. Okay, for the square thread or square thread. Okay, so as we already realized that the power screws combined with a nut, right, which can supply a load for raising or lower, right, and this interface between the nut and power screws with different types of the stress. Okay, so the first stress is that the distributed load applied to the surface of the thread. Okay, or we can call it a bearing stress, and this reaction, the reaction applied to the power screw is the actual stress, right? The actual stress, right? The actual stress. Okay. And there's the critical stress element located at the roots of each thread. Okay, right here. So what's the stress distributed at this critical element? Okay, so that's the main topic we're gonna discuss today. Okay, so first, I have to define some dimensions. First is the mean radius, okay, which is equals to the mean diameter divided by 2. Okay, and the mean diameter is the diameter of the center of the each thread or each tooth. Okay, you can say it's the mean diameter. Okay, mean diameter. Okay, and okay, so uh when this power screw rotated, right, as what we mentioned previously, there's the reaction force, right, which is the reaction force corresponding to the force applied to each thread surface. Okay. Okay, so for the actual loading, if we look into the small, tiny element, the tiny critical element, okay, so its stress distribution is the sigma y. That's the actual loading, right? That's the actual loading applied to that critical element. And sigma y equals to minus f divided by the area. Area equals to pi over 4 times the dr square. Okay, so for this power screw, the first loading or stress that we are going to discuss is the actual loading, right? The actual loading. Okay. Okay. So for this second stress we're going to discuss is the bending stress applied to that small critical, tiny critical element. Okay. So if we look into the thread, okay, and the engaged number of the thread in this case, okay, in this case, the NT equals to 2.5, or we can say the total thread. Sorry, the total number of the threads is 2.5. Okay, from the point A to point B. Okay, so we have two completely two terms of the threads, and with the one or with the half, right? Half turn of the thread, right? And the load will distributed on the surface. Okay, the load will apply to this surface. So when we stretch, I mean, when we extend, we stretch the thread AB to form a rectangular. Okay, so okay, just extend it, just expand it. Okay, to form a rectangular bar, right? So the surface, the thread surface, is subjecting to a distributed load. Okay, so we can define the length of this AB bar or the AB rectangular bar is NT times pi times dr. Right? Okay, so if the cross section is a square, okay, in this case, because as I mentioned previously, this is the power screw with the screw thread, right? Square thread, sorry, with the square thread, right? So we can assume that the distributed load is the point load applied to the center, right? At the center position. Okay, so we can simply calculate the moment applied to this critical element, right? So the distance here is half of the P. P is the pitch, right? P defines the pitch. Therefore, we can know the moment applied to that critical element equals to Fp over 4, and the y equals to P over 4, right? So the P is the y is the distance from this neutral axis to the surface in this case. Okay, because the cross section is square, therefore the moment of inertia I equals to 1/12 times the BH cube, right? Okay, so we can plug those M, Y, and I into this bending stress equation. Okay, bending stress equation, right? Okay, so we can get the bending stress applied to that critical element with a distributed load. Okay, with a distributed load. Okay, so the next stress is the shear stress. Okay, so if we just split, we take into part of the thread and the shaft, right? As we already know, this shaft is 2.5 times number of the thread, right? So we can just suppose we can separate the thread and the shaft, okay? And there's a shear stress is applied to the interface between them. Okay, there's an interface between the thread and the shaft. Okay, when a torque applied to this power screw. Okay, when the torque applied to this power screw, there's a shear stresses in between. Okay, in between. Okay, and this the torque will equals to V. The V is a shear force, right? The shears times to the radius. Okay, the radius. Okay, the radius. Okay, the V is the tangential shear force, right? And we can rearrange it to get the shear force equals to 2T over dr, right? 2T over dr. Okay, and the area of this the rectangular bar is, sorry, the cross section area of this rectangular bar equals to BH, right? Equals to the surface of this rectangular bar equal to BH, and the B equals to the NT, the number of the threads, right? Times the pi times dr times the P over 2, right? We get the surface of this thread, the surface area of the thread. Okay, and from the definition of the shear stress equals to force divided by area, right? The force divided by area. So we get the force here, right? The shear force divided by the area, right? The area here, right? Area should be on the other side. From the area should be located in side view, right? Okay, so we can get the shear stress in between these threads and the shaft. Okay. Okay. And next stress applied to this power screw is called the transverse stress at the center of the roots of the thread. Okay, so what is transverse shear? So what is transverse shear? You still remember that? Okay, so previously we discussed the bending, right? The bending stress at this critical element, right? So if you still remember the bending stress, we have the beam applied to a bending, we have the element with a bending, right? Sorry, let me apply, let's modify its direction, sorry. We have bending, right? So we can get the stress distribution, right? If you still remember that, right? This is the stress distribution of the bending stress. And for the transverse shear stress, which is the maximum transverse shear stress, is located at the center right here. And on its surface, the transverse shear equals to 0. Okay, and NA represents the neutral axis. The neutral axis. Okay. Okay, so the top of the roots right here, the shear stress, the shear stress here equals to 0. Okay, the shear stress equals to 0. And the maximum transverse shear stress, if you still remember it from your materials mechanics course, the shear equals to 3 times the shear force divided by 2A. Okay, therefore we can get the transverse shear. Okay. Okay, so of course we can just look into a small element within the any position of the cross section to figure out its shear stress distribution. Okay, shear stress distribution. Okay, so this is what we are looking at. Okay, the transverse shear. Okay, the transverse shear. Okay. Okay, so the next stress that we're gonna take into account is the torsion, right? So for this power screw, of course, we must apply a torque, right? And this power screw must be subjecting to torsion, okay? Subjecting to torsion, right? If we look into the shaft, what is its torsional shear stress is. Of course, you guys must be familiar with that, right? If you already learned this from your mechanics materials books. Okay, so this torsion stress equals to tau equals to T, the torque times the C, okay, C divided by the polar moment of inertia, right? And in this case, the C is half of the diameter, right? The shaft diameter, okay, okay, and this is the R, right? And the polar moment of the inertia of the shaft or circle, right, equals to pi over 32 times the d power of 4, and we get the shear, the torsional shear stress equals to, right, the 16 times the torque divided by pi dr cube. Okay, pi dr cube. And we already know the highest, the torsional shear is located at the surface of the shaft. And at the center of the shaft with 0 torsional stress. Okay, 0 torsional stress. Okay. Okay. So it's just a little recap of your materials mechanics course. Okay. Okay, so now let's look into what's those stresses applied to this power screw. The main stress applied to the power screw. Okay, so the first is the actual loading, right? Actual loading and the bending stress, right? The bending stress right? The maximum stress concentration will located at the critical element, right? Critical element. And the pure shear. And the pure shear, which is defined between the what? The interface, right? The interface between the thread and the shaft. And the final is the torsional shear, right? The torsional shear. And you will feel weird that why this transverse shear is not taken into account. Well, because it is not the main stress that causes this power screw fail. Okay, it's not the major reason or the major stress concentrated to cause power screw fail. Okay. Okay, so we know the torsional shear stress and this actual loading, actual stresses on the body. And what else? The bearing stress, right? The bearing stress is defined as the surface, right? So the distributing on this surface, distributed load applied to this stress, and which is the opposite force to this actual loading. Actual loading. Of course, it's still not the major stress to cause the power screw fail. Okay, okay. And it's the bending stress, okay, and transverse shear. And this is not also the these two are not the major stresses to cause the power screw fail. Okay. Okay, so the thread formation in screw knot combination, okay, that we already discussed previously. The power screw thread is in compression, right? Of course, it's in compression, causing the elastic shortening of the screw thread pitch. And engaged knot is in tension. Power screws is in compression, and the knot is in tension, causes the elastic lengthening of the knot thread pitch. Consequently, the engaged threads cannot share the load equally. Okay, so it's an important idea is that the engaged thread cannot share the load equally, and experiments indicate the first threads carry 38% of the load, and the second thread takes the 25%, and the third thread takes the 18%, until the seventh thread is free of the load. Okay, and to find the largest stress in the first thread of screw knot combination, the rule of thumb is by using the 0.35 F in place of the force, and set NT equals to 1. The total number equals to 1. Okay. Okay, so let's just return to this stress distribution applied at that critical element. Okay, this critical element. I'm not going to deeply discuss each stress component, right? Or I don't want to focus on that because I think your materials mechanics course already taught a lot of it, right? Okay, so for the design point of view, we already know that for this action loading, for the bending stress, for this pure shear, and for the torsional shear, right? And we also consider the critical cases, the critical element loaded at the first engaged thread, okay? Loaded at the first engaged thread. We consider the critical case. That is the first thread that takes the highest portion of the loading, right? So the first engaged thread, right? Take the 38% times the loading times the load, right? And the 7 without any load applied to it, right? Okay, so therefore we can just replace the force with the 0.38 F and set NT equals to 1. Okay, so for example, we can replace this F with the 0.3 AF and NT equals to 1. Similarly, we can replace the torque equals to 0.3 AT and NT equals to 1. Okay. Of course, this F can be replaced with the 0.38 F. Okay, so that's the critical case we are gonna take into account. Okay, take into account. Okay. Okay, so from this failure criteria point of view, we have to recap what we learned is called the von Mises stress, sigma prime, right? So sigma 1, sigma 2, and sigma 3 represents the principal stresses, 3D principal stresses. Okay, and the 3D stresses element are subjecting to the stresses with sigma x, sigma y, tau y, z, and tau z x. Okay, and we define the sigma 1 is not equals to sigma 2, it's not equal to sigma 3, and it's not equals to 0. Okay, and then we can define the von Mises stress in terms of the 3D stress element. Okay, so there are two in this slide present two presentation of the von Mises stress, right? One is with the principal stress, sigma 1, 2, 3, and the other is present in terms of the sigma x, sigma y, and tau x, y. Okay, that's the 3D stress element. Okay, and then we can figure out the principal stresses by drawing the Mohr circle, right? The Mohr circle. Okay. And as we mentioned, the top of the roots plane, which is stress equals to 0 in this case. Okay, if this is the z direction, right? So this z direction should be on this surface. Okay, this surface or this surface, right? So you can imagine that if we have the shaft like this, right? And we have the small element, and this z direction is perpendicular to this surface. Okay, this is surface. Therefore, can define the stress of that small element. Okay, right? Okay, the small element. Okay, right here. Okay, and then we can compare with the critical element whose stress distribution located at here. Okay. Okay, I'm not going through the detail of this, but I just want to know the surface, the top surface of the roots plant, the transverse shear equals to 0. Okay. Okay, so now we can consider the stress element at the top of the roots, plane. Okay, right here or here, here. Okay, so of course the actual stress still, right? Because we have the actual loading and the tau xy equals to 0. And of course we have some bending stress, right? On this surface and this element, right? So the critical stress here and the top of the root plane right here and here and here, right? Or here, sorry, right here. Of course, at that element locations, there must be a bending stress applied to it. Okay, there must be a bending stress applied to it. Okay, of course, the actual loading sigma y and the torsion, right? And the torsion. Okay, so for this stress element at the top of the root plane here, we have to take those stresses into account: bending, axial, and torsion. Okay, and the differences with the stress element compared to the critical element. Critical element, as let me change the color. It's right here. Okay, right here. Okay. So we can apply those stress to the sigma prime, the von Mises stress. Right? What we get? We can get its sigma prime, and we can use any failure criteria to define its safety vector. Okay, define safety vector. If you still remember that we already told the stress envelope, right? The envelope to define the safety vector of based on each criterion. Okay, the distortion energy method or the maximum shear stress and so on. Okay, and there's the next some type of the bolt. I think you guys can just study by yourself. Okay, so just filester, flat, socket, and so on. Okay, just skip it. Okay, so I think you guys can study by yourself. Okay. Okay, and next we're gonna discuss the torsion load bolt joint. Okay, the joint defined as we have the bolt and nut and those plates or member. Okay, the member. Okay, and there are some definition of the geometry and dimension. For example, like the Greek length L, including everything being compressed by bolts, preload, including washers. And the washer under head prevents burrs at the hold from lodging into the fillet under the bolt head. Okay. Okay, and the 6 head cap screw in tap hold used to fasten the cylinder head to the cylinder body. Note O-ring seal not affecting the stiffness of the members within the grip, and O-ring part of the thread length of the bolt contribute to the effective grip L. Okay, so the effective grip length L is defined where from the only part of the thread, right? So you have to depends on the definition of the screw thread type. Okay. Okay, so this is the definition of the effective grip length. Okay, it's the definition. For screw in tip hole, effective grip length is if the D, what is D? The major diameter or say the nominal diameter of the bolt, the thread. Okay, it's greater than T2. What's the T2? Is the length, the thickness of the member 2, the second member, or the second plate. Okay, and this grip length equals to H plus the T2 over 2. The H defines the washer thickness plus the thickness of the first member or the first plate, right? The H, right? The H plus the T, half of the T2, right? Half of the T2, right here. And if the major diameter is less than T2, or say the T2 is greater than the major diameter, the effective grip length equals to H plus the half of D. Okay, the half of D. Okay, so now we are gonna look into the concept of the stiffness. Okay, we can define the bolt and the nut to define their stiffness. To define their stiffness. Okay, so the function of the joint, including the bolt and nuts and the members, is to fasten, right? We're gonna clamp, we're gonna fix 2 members together or multi-members together, right? To fasten, right? So during the bolt preload, when the bolt preload, bolt is stretched. Okay, without any external loading, when we tighten, when we tighten those bolt and nuts, the bolt itself is stretched, and the member in grip are compressed, right? So this bolt itself must feel, okay, being stretched, okay? And the member, the plates, the two plates, they must be feel, okay, I'm being compressed. We're gonna be squeeze. We're gonna compress it, okay? Okay, when the external load is applied, what is the function of the external load? That is the load we're gonna separate the members. We're gonna separate the member 1 and member 2. Okay, so when external load P is applied, the bolt stretches further. Without external load, the bolt feel being stretched. And with the external load, the bolt feel will I am being stretched further. And the member in grip uncompressed. That means it's not fastened so tightly. It's become a little bit loosened. You know what I'm saying? Okay. So for the member, you feel okay, I'm be uncompressed. Okay. And the joint can be modeled as the soft bolt spring in parallel with stiffness member spring. Therefore, can consider each component like the bolt, the knot, the member with their own stiffness. Okay, with their own stiffness. Okay, okay, I think the course will stop right here. So next, I'm gonna introduce the more details of the stiffness of each member bolts or not. The final part of this section, I'm gonna just introduce some concept. We can regard those components, bolts, nuts, and members with their own stiffness. We can regard them as springs. Okay, so I think today's course will stop here. Okay.